Look at the International Space Station, orbiting 240 miles above the Earth. Up here, astronauts live and work inside an artificial bubble of pressure, completely isolated from a deadly, airless environment. Now, imagine a micrometeoroid traveling at orbital velocity strikes an astronaut on a spacewalk. It creates a tiny puncture in the suit, venting precious oxygen out into the blackness. The astronaut is suddenly depressurizing. Pop culture tells us what happens next. The body instantly freezes solid, or massive pressure differences cause the astronaut to explosively burst. Fortunately, neither of those Hollywood myths are true. The reality, though, is far more lethal. The immediate threat to an astronaut isn't the freezing temperature of the cosmos. It is the absolute, terrifying absence of atmospheric pressure. Human biology evolved at sea level, perfectly adapted to push back against the constant 14.7 pounds per square inch of pressure. But as you move up, pressure drops. At 62,000 feet, you hit the Armstrong limit. Up here, ambient pressure falls to less than 1 pound per square inch, so low that water boils at the normal temperature of the human body. Back in orbit, the moment our astronaut suit pressure drops to zero, they cross that exact same physical threshold. They are exposed to a near vacuum, and a strict 90-second biological countdown to death begins. Without that invisible weight pressing against our skin, our biology immediately turns against us. An artificial pressure envelope is the only thing keeping those internal fluids intact. In the first few seconds of decompression, human instinct is to hold your breath. That is the worst possible reaction. In a vacuum, the trapped air expands violently, tearing lung tissue. Even exhaling, the lack of external pressure reverses gas exchange. The vacuum sucks oxygen out, and blood flowing to the brain becomes completely devoid of oxygen. This sudden, total oxygen starvation shuts down the central nervous system. Right at the 15-second mark, the brain simply turns off, and the astronaut blacks out. The loss of consciousness means the astronaut can no longer patch their suit or maneuver back to the airlock. They are entirely reliant on a rescue crew. Between 15 and 30 seconds, a severe physiological reaction called ebullition takes over. Because there is almost zero pressure on the body, water vapor trapped inside tissues starts to boil. This expanding vapor creates massive pockets of gas under the skin, rapidly distending the human body to nearly twice its normal volume. We know exactly what this looks and feels like because it has happened on Earth. In 1965, NASA test subject Jim LeBlanc was inside a massive vacuum chamber, testing a pressurized suit, when his air supply hose suddenly detached. He was exposed to a near vacuum for roughly 30 seconds. Before he lost consciousness, he reported his final chilling memory, the physical sensation of the saliva boiling directly on his tongue. If exposure continues past 30 seconds, the cascade accelerates. The expanding vapor forces the cardiovascular system to collapse. Blood circulation fails, and by 90 seconds, the heart stops completely. These heavy, cumbersome spacesuits serve a singular, critical purpose. They are engineered wearable Earth atmospheres, maintaining the pressure required to keep bodily fluids liquid. Let's return to our astronaut. At 45 seconds into the exposure, crew members drag them into the airlock and violently throw the repressurization valve, flooding the chamber with air. It is easy to assume the astronaut is dead, yet medical literature proves otherwise. As long as normal atmospheric pressure is restored before cardiac arrest sets in, extreme vacuum exposure is highly survivable. When technicians repressurized the chamber in 1965, Jim LeBlanc walked away with nothing worse than a sore ear. 17 years later, another technician survived well over a minute of vacuum exposure and fully recovered. Treating survivors of severe ebullition involves placing them in a hyperbaric oxygen chamber. The intense pressure forces the trapped vapor bubbles back into a liquid state and treats the resulting decompression sickness. The human body possesses incredible resilience against the void, but that resilience only holds up if the strict timeline of rapid repressurization is met. Understanding these extremes becomes vital as space agencies plan long-duration missions to the Moon and Mars, where help is millions of miles away, and spacecraft must protect against depressurization perfectly. Current spacesuits are miniature, wearable spacecraft, utilizing 6 decades of safety data to counter the physics of the Armstrong limit. Leaving our atmosphere places our water-based biology in direct conflict with a vacuum, where our survival relies entirely on the mechanical reliability of our suits. Space is a hostile void that wants to tear us apart, and our engineered environments are the only things standing in its way. If you want to see more of the science keeping us alive out there, make sure to hit subscribe.